Look at this two-dimensional plane sitting inside a larger three-dimensional space. Suppose we have a linear mapping, a straight-line graph, defined only on that small, flat subspace. The challenge is extending this mapping, stretching it to cover the entire space, but with a strict condition. The new extended graph must remain permanently trapped beneath that translucent, glowing bounding canopy. These mappings are linear functionals, tools that map complex vectors down to simple numbers. Without them, we would have no way to extract numerical information from the space. We collect these tools into what's called the dual space. To analyze a space's geometry, we need to know that this dual space is populated enough to actually measure its structure. If you only have a functional defined on a small subspace, you might think you can just assign a value of 0 to everything outside of it, but doing that immediately breaks the linearity of the function. In a finite dimensional space, you can construct an extension step by step using a basis. In infinite dimensions, however, that approach falls apart. Without a finite basis, trying to force an extension point by point can cause the slope of the functional to blow up. The mapping becomes infinitely steep, breaking the boundedness condition that makes it useful in the first place. This means infinite dimensional spaces need a guaranteed mathematical mechanism to extend a functional safely. We need a way to ensure the mapping covers the entire space while staying strictly below a specific ceiling. That ceiling is formalized as a sublinear functional, denoted as p of x. It operates under two rules: subadditivity, meaning the value of a sum is less than or equal to the sum of the individual values, and positive homogeneity, meaning scaling the input scales the output proportionally. Geometrically, these rules shape the functional into a cone-like canopy expanding outward from the origin. This brings us to the Hahn-Banach Theorem. It states that if we have a linear functional defined on a subspace, and it is less than or equal to our sublinear canopy, we can extend it to the whole space. And crucially, the extended functional will still obey that exact same boundary condition everywhere. By keeping the functional pinned beneath this sublinear canopy, the theorem provides a safety net. It guarantees that the norm of the functional is preserved during the extension. The mapping will never spiral out of control. To prove this, we start by collecting every single valid extension of our original functional into a set. We order this set by inclusion, creating a chain of expanding domains where each functional is an extension of the previous one, f contained in G1, contained in G2, and so on. Because every chain in this set has an upper bound, Zorn's lemma guarantees the set must contain a maximal element. We will call this the maximal extension, f tilde. But we have to be precise here. In the context of Zorn's lemma, maximal only means the functional cannot be extended any further within our specific set of rules. It does not automatically prove that this maximal domain actually covers the entire space X. Look at this maximal domain. To prove it covers everything, we assume the opposite. Suppose the maximal domain is not the entire space. That means there is at least one point, y1, hovering outside of it. By adding y1 to our domain, we construct a completely new, larger subspace. The challenge now is finding a way to assign a value to this new dimension. We have to map y1 to a scalar without forcing the extended functional to pierce through the sublinear canopy. We do this by relying on the subadditivity of our canopy. The algebra yields a pair of inequalities. We get a lower bound and an upper bound pushing against each other. Because the original functional was strictly trapped by the sublinear functional, these two bounds never cross. They leave a distinct mathematical gap. We can pick any constant c that fits cleanly inside this gap. By assigning that constant to our new point y1, the functional successfully extends by one full dimension, all while staying strictly legal under the canopy. This is our contradiction. We just successfully extended a domain that was supposed to be maximal. Since the domain can always be extended as long as there is a point outside of it, our initial assumption was false. The maximal domain must already be the entire space X. Because we can always define a functional on a single vector and then extend it out one dimension at a time, this theorem guarantees that every non-zero vector can be reached by a continuous functional. We are no longer just extending existing mappings. We have a way to populate the space with them from scratch. This translates directly into geometry. If you have a convex set, like this 3D shape, and a point located outside of it, The existence of these functionals allows you to define a flat hyperplane cleanly separating the two. In optimization theory, this separation allows us to solve complex problems by analyzing their dual costs. In quantum mechanics, it provides the structure to define physical observables as operators acting on functionals. The Hahn-Banach theorem ensures the dual space is never empty. It provides the essential vocabulary mathematicians use to describe and navigate infinite dimensional environments.